Well, hello everybody. Bob here in Torrington, in our classroom actually. I've heard from most of you, and I think you're kind of getting settled into the way that we're going to attempt to finish the semester. I'm at a weird angle here because I set up in our classroom a little way to make a video or two to try to help you guys through a couple of the sections that we'll be working through that probably could use just a little bit of assistance on some of the things that are going on. So I'm going to tip the camera down here in a second and start talking about section 6.2. I'm assuming probably, and you should assume by the time you start watching this video, that you have worked pretty hard on the homework in section 6.1 and tried to understand that. I'll do a little bit of reviewing at the start here, but my purpose is to get us into section 6.2, understanding the terminology of linear programming, and I'm going to go ahead and move around and begin that now. So here you see I prepared a couple of slides or a couple of pieces of paper where I took some notes from section 6.1, and what we got out of section 6.1, you did hopefully, is the definition of what we would call a standard maximum problem or a standard maximization problem, and I've kind of written it in that form. I didn't put a ... here at the in this constraints column, but there could be any number of constraints. The standard maximum problem has coefficients of our variables. The constraint, the numbers on the right hand side of the constraints have to be positive. We'll see later that you take other measures when those aren't. In section 6.1 you also got the beginning of the idea of slack variables. We label those as S1, S2, S3. You'll see a couple of those appear in my equations down here in just a second. But we use they're named slack variables because we use them to take up the slack in the inequalities that we start with in order to make the inequalities become equations. And we also use them to keep us in the feasible region as we understand when they're allowed to be positive and negative, and those issues that come up here in shortly. So we began in section 6.1. They would have presented you with what I would call a standard an I system. This is their terminology. That stands for the inequality system. So there's our non-negative constraints. We start off with less than inequalities. All the coefficients are positive in this system. So if you remember, there were theorems that we covered in chapter 5 that kind of talked about some of those issues. From the I system, we form the E system. So right here below, this is called the E system for equations. And in section 6.1, the discussion to learn basic terminology, but learning how to solve by something called the table method, we were to understand that with our E system here, that their solutions occur wherever these four lines, so there really are four lines in our XY plane that are intersecting each other at different places, and those lines have to intersect at, or our solution points will lie at those points where two of our boundary lines intersect each other, or more possibly, as you remember. So what you were really doing in section 6.1 was alternately making two of these variables, of the four variables that I have here, be 0, and then finding the solution. If you set any two of these equal to 0, you can solve for the other two variables, creating what we called an ordered quintuple in this case, because there were four. And in section 6.1 we learned that if all four of these variables are positive, then we've found what's called a feasible solution. And what I just kind of did, there's a procedure on page 290 which led to a theorem called Theorem 1 in section 6.1 that said, let me paraphrase it here for you just a little. I'll move my hand out of the way. Theorem 1 said that, I apologize, that if an optimal solution exists, then it exists at one or more of the basic feasible solutions. So we learned how to find feasible solutions or basic solutions, and Theorem 1 explains the basis for all of linear programming that says that one or more of the basic feasible solutions is our optimal solution if it exists to this system of inequalities that we started with. So I'm going to jump forward a little bit. I was just going to try to remember to say a couple of things there in that short little space about section 6.1 as you began there, but let me move forward into section 6.2 where we start learning about how to solve the standard maximization problem with constraints of the form less than or equal to by what we call the simplex method, which is, we'll learn, programmed into your into Excel. So our job in the course of what we learn over 3 sections here is to understand how you would use software, for example, to solve maximization problems, optimization problems if you were in a business setting. Okay, so I'm going to start in section 6.2 and just kind of jump right into it, where I'm going to follow an example to get all of the terminology and get us all into and up to the what we call the initial simplex tableau. So that's the purpose of this discussion here, which I'm going to try to remember to cut off in about 15 or 20 minutes here. So I'm talking quickly or trying to make sense in a fast way. Apologize if it doesn't. So remember to ask questions, of course, if I can help. So we start with, and I picked a super simple example to begin with. I have 2 constraints. Notice the second one's a little bit odd, x2 less than 2. So I'm starting with a kind of a simple system to solve, however, maybe made a little more complicated by the negative coefficient in the first constraint here. But I'm gonna, I think I picked a weird example to work on, but this one ends up having no solution, as you'll see later. And I can explain to you one of the reasons why you know there's no solution. And so it turns out to be not a bad example to work our way through. So we began with, and let me cover this up with my pen. We began with the inequality system, the I system, and we made the E system. So to each one of the constraints, negative 3x plus 4x2 less than 12, I add a slack variable. So every constraint, you add a slack variable, and that allows you to turn it into an equation. So as you rewrite your I system into the E system, there's step 1, add a slack variable to every constraint, x2 plus s2, that's my second slack variable, and you should have one of those for every constraint that you have in your problem. And then you've turned these into equations. We have, if all the variables have to be positive, so in my system that I started with right here, x1, x2, s1, s2 from the E system to the I system have to be positive in order for the solution to be feasible. I talked about that a minute ago. Okay, what we do to begin the simplex method is we add the objective function into the E system in the form everything on the left-hand side and 0 on the right-hand side. So if I took our initial objective function, maximize p equals 2x1 plus 3x2, I subtract 2x1 and subtract 3x2 to both sides. So the way I rewrite my objective function is negative 2x1 minus 3x2 plus p is equal to 0. And then I put it into with the other 2 constraint equations, and I make it the third constraint. So the third constraint of since I had 2 constraints, the third one becomes the objective function. If you had 3 constraints, the fourth constraint would become your objective function. In the third constraint that I've written here, p is always, in the simplex method, is always chosen to be a basic variable. So it's always in the solution, and sometimes we'll see a weird case or two. P turns out to be a negative number, especially when we start minimizing. You might see that that'll happen for sure, but it's the only one of our basic variables that can be negative. So this system that I've created, the E system that I begin to make the simplex method from, has 3 basic and 2 non-basic variables. So remember, the non-basic ones are the ones that are set equal to 0. The basic variables are the ones that are in the solution. And I know you guys were doing homework about that because I slipped in and did a little bit of it myself. So in section 6.2 we cover a theorem that says if all of the variables of a basic solution, so one of those ordered quintuples or ordered 5 tuples that I've written, are non-negative, so if all of the variables are non-negative except possibly p, then the solution is called a basic feasible solution. And we're guaranteed that the optimal solution must be at a basic feasible solution to the initial system. So I'm going to do some of the work in front of you here instead of having it all pre-prepared. I'm going to take my initial system or my E system that I wrote just a little bit ago. So my E system that had P, the objective function included, and I'm going to put it into a matrix. And I started working on it before, and then I thought I'd stop and do it while you were watching. So maybe I don't know if it'll help for you to see where I'm doing it, but there's the old E system, and here I'm going to write across the top, and I already made a slight mistake, but I'm going to fix it. Across the top, I'm going to put the decision variables, so x1, x2, the variables that I'm trying to decide about to solve my problem. And then come the slack variables, s1, s2, and you're going to have, remember, one of those for each of the constraint equations that you have, or constraint inequalities. Then later on we'll have columns for artificial variables and some other things. In our case here we have one more variable, we have the variable p, and then we, like we did before with augmented matrices, we make a dashed line here, and then we put the right hand side over on the other side. So my equation has coefficients -3, 4, 1, 0 s2, 0 p, and then 12 on the other side. So these variables are 0 right now, and 12 is on the other side. So I'm forming what you're going to call the initial simplex tableau as I'm carrying on here. Inequality number 2, x2 plus s2 equals 2. Looks like this. There's no x1s, 1 x2, 0 s1, 1 s2, 0 p, 2. Right? So the coefficients of s1 and x2 and s2 were both 1 and 2 on the right hand side. Then another dashed line in the simplex tableau right here. They make it a solid line, I think, perhaps, but this is the underneath the line where we put the objective function equation that we made to start to form our initial system. So down here below, go -2, -3, 0 s1, 0 s2, 1 p, and 0 on this side. All right, I'm going to go ahead and label the rows and the columns of my initial system that I've just written right here. The rows and the columns are labeled. Maybe I'll notice a couple of things here as I'm getting started. Notice the identity matrix is listed right here. At this point, as you got through section 6.1, remember x1 and x2 are neither one in the solution. Remember the variables that have not all zeros in the column except for a 1 are set at value 0. So putting the matrix into this initial in the initial tableau here sets the initial solution at x1 equals 0, x2 equals 0, s1 equals 12, s2 equals 2, and p equals 0. So in other words, the initial starting tableau sets the starting point at the origin, and the whole process leads to the direction of greatest increase in order to find the optimum value. I'm going to label the sides over here. Right now we have our basic variables are s1, s2, and p. The basic variables, the ones that you see on this side, are the ones where the ones in the columns are. So P is a basic variable right now. I didn't need to put a P1. S2 is basic, and S1 is basic. So all of these ones that have ones are basic, and they're in the solution. What else could I say about this? The method is going to start here in just a second. They're going to ask you to do a little bit of labeling rows and columns, or talk about entering and exiting variables. I'm going to proceed on here just a little bit. The columns, I'm sorry, lost my place here, what I was going to talk about. So what we're about to do is look for a way to increase this value, the value that's down here. The Simplex method tries to make this value be as big as possible. And the way that it starts working is by pivoting around bringing x1 and x2 into the solution, taking away slack, moving out into the feasible region. Remember our basic standard optimization problem, maximization problem, has a bounded feasible region. What we're trying to do is get out to the farthest, most outreach point that our objective function line, remember how that all worked before we had spring break, where our objective function line intersects the feasible region. So the method is trying to move outward in the direction of greatest increase towards the farthest point that it can touch with with lines of constant profit, if you remember how that all kind of went in the earlier chapters. So what we're going to do, let me name a couple other things. This row is called the indicator row. So this is the row that kind of tells you how to pick the pivot, to get the process of beginning to pick the pivot column. If we're going to try to find a better solution, we begin by start at the indicator row. And let me label a couple of other, actually I can go ahead and find the pivot element for you right now. So it begins, I'll describe the process. You look in the indicator row for the biggest negative value in that row. If there are no negative elements in this starting row, then you're at a solution, you're at a basic feasible solution, and you can't improve it. So if a solution exists when there are no more negative numbers in this bottom row, then that is the optimal solution. So our goal is to have no more negative numbers down here. We begin picking the pivot element by finding the pivot column, and the pivot column in this case would be x2 column, because that's the biggest negative number in this bottom row. So this then becomes what they call the entering variable, and I'll talk about the exiting one in just a second, but this is the variable that's going to enter into the solution. Maybe I'll make this little note. If there are no non-zero elements up above here, or positive ones, so non-negative elements, there can be a zero, but if there are no positive numbers up here, up above, then you're finished and there is no solution to this problem. All right, so if this was going to be my entering variable and I looked up above the line right here and there were no positive numbers, then I'm done. I'm at a finishing place and there is no optimal solution. Okay, so that's one thing to note as we go along. I'll describe the flow chart maybe before I quit here. All right, now I'm going to pick the pivot row. The theory behind why you pick the pivot row is you're trying to add the most. So I'm going to be able to increase my profit by adding x2s the most. If you go back to the original objective function, remember 3, oops, I picked the wrong paper. 3 was the slope of or 3 was the multiplier of the profit function. So the reason that you pick this one as negative is that increasing x2 by 1 unit increases the profit more than picking 1 unit of x2. So that's why we pick the biggest negative number after those have been subtracted over to the other side. Okay, so that's my entering variable. Now what I do next allows me to find the pivot element by going in the direction where I can add the most at the least amount of unit cost, maybe is a way to say it. So the way that we find that is we take the number that's over here on the left-hand side, or on the right-hand side, and we divide it by the number that's in the pivot column. So I take the number 12 that's over here and I divide it by the number that's in the pivot column. And so this number divided by that number, and this number divided by that one. If this number over here is negative, you don't need to worry about it because that's not possible. So no dividing by negative numbers in this process, only if there's a positive number in this column. So I divide 12 by 4 and 2 by 1, and the one that I pick is the smallest. So 4 goes into 12.3, 1 goes into 12.2, so this number is the smallest number. That makes this be the row, the pivot row, that I will use. This will be the one that I use to pivot on. So the intersection of the pivot column, or the entering variable, and the smallest one of those quotients becomes the pivot element. So this element becomes the element that I perform what we call a pivot in the simplex method. This becomes the pivot element. All right, and what a pivot step, as you'll come to learn, and there's a couple of other things that we add into the mix, but a pivot step is just like what we did in chapter 4 when we were doing Gaussian reduction. A pivot step has you turn this value into a 1 and get zeros in the column, the other elements of the column that you're talking about. So in this case right here, 1 is going to, or x2 is going to come into the solution, and s2 is going to exit the solution. So this variable right here is going to be the one that they call the exiting variable, and I'll relabel later, but the entering variable is the pivot column that you just picked. The exiting variable is the pivot row from where it was before you started. So that sort of terminology they ask you a question or two about. That's how those values are determined. The pivot, the entering. I was trying to decide what I should do here next, and I think what I'm going to do is I'm going to do a pivot step. So I'm going to, we've set up the initial tableau, I've identified the pivot element, and now I'm going to perform a pivot step. I think I can do it in just a minute or two here without being too boring, but it might be kind of boring. But you guys kind of missed that. I used to wake up and come to class, and I would try to put you back to sleep. So what I'm going to do is, maybe in the place where it is, I'm going to perform a pivot step. The process is, like I said, just like Gaussian elimination. There's an interpretation that you do after performing a pivot about whether you've achieved an optimal solution, whether no solution exists, and that's in a flow chart on page 307 that I'll show you here in just a minute after I get a little further. But I'm going to perform a pivot step. So I'm going to rewrite my matrix. And the pivot row, if this element right here was not a 1, then I would divide row 2 by whatever that value was in order to make it be a 1. But since row 2, maybe I'll relabel my variables here. That sometimes if I do this part, it helps me keep things straight. So I'm going to label my rows S1, S2, P, and the other one to try to help me keep things kind of lined up from where I was up above. So S2 was equal to 1, P was 0. So I didn't change that row. I'm going to use this one in order to get zeros in the rest of that column. All right, so if you remember how that worked, I need, in order to get a 0 in this space, I need to multiply row 2 by -4. So here's negative, well, I should put it down here, -4 row 2s. This is the way I did it in class. This will remind you of home. So I'm multiplying 0, -4, 0, -4, 0, -8. And the step that I'm going to perform is row 2 or row 1 plus minus 4 row 2's, and I'm going to put that back into row 1. So I'm going to add the original row 1 to minus 4 row 2's and put that back into row 1. All right, so here hopefully I do that straight. 0 plus negative 3, negative 4 plus 4. I better get a 0 here, that was my goal. 0 plus 1, negative 4 plus 0. Negative numbers can start appearing here. Remember, these columns that have not all that have all these extra numbers in them, those are the non-basic variables. Those are the ones that are 0 in your solution. 0 plus 0 and negative 8 plus 12 is 4. All right, maybe I shouldn't have put that so close down here, but I used that row, negative 4 row 2's added to row 1 in order to get this row. And I'm going to do that one more time. I need 3 row 2's. So 3 times row 2 here added to the original row 3. And I'll substitute that back into row 3. But I'm going to concentrate here, 0, 3, 0, 3, 0, 6. Okay, and I'm going to add this. I'll write it down here, what the step that I'm going to do. 3 row 2's plus row 3 back into row 3. Okay, so that row that I just made, I'm going to add back here. That makes negative 2, 0, like it better be. That's the row that we were trying to turn into, or that we were trying to add into the solution. What we've done is we've made x2 be a basic variable, so it's now one of our solution variables. X2 is equal to 2. So we've actually, if you think about the picture, we've moved up to the boundary line where x2 has to be 2. So we've moved up to its maximum value. Let me finish here. 0 plus 0, 3 plus 0, 0 plus 1, 6. All right, so there, I'm going to scribble that out so I don't get confused myself. So I performed one pivot operation. I brought x2 into the solution. If I were labeling the rows here, the other variable that's still in the solution is s2, so, or s1. So this is the s1. This is always the p row, the p variable. Remember, p is always in the solution, so this column should always stay as 0, 0, 1 as you work through the process. My solution right now is s1 is equal to 4, x2 is equal to 2, x1 is equal to 0, x2 is, or s2 is equal to 0, and p is equal to 6. So I increased the profit up to 6 by going, if you think about the geometry of what's going on, I moved up to the boundary line. Remember, one of my constraints is that x2 has to be less than or equal to 2. So I kind of moved up to that line, and now what I'm going to do is kind of move along it until I use up all of my extra slack that I have left making x1s. All right, so we already, if you kind of see geometrically what happened, we've performed one pivot. All right, they ask you to analyze and write the solution sometimes, so that's why I did this part right here. So sometimes they ask you to write from looking at the tableau where you're at, what is the solution? The solution comes from where the ones are. S1 is equal to 4, and P is equal to 6. X2, there's the other one, is equal to 2. All right, the other ones, we've set them equal to 0, and we did increase the profit by making that little maneuver. All right, I'm going to keep going here on this particular problem because another pivot we haven't remember in the indicator row down here, until there's no more negative numbers, you haven't reached an optimum solution. So because we still have a negative number in the indicator row down here, we haven't gotten to an optimum solution yet. And I think sometimes in their terminology they say an additional pivot is required. All right, so this -2 down here is going to be my next pivot element, and maybe you can help me here. I'll go ahead and pick it right here where my actually, you know what? I back up and I see it happening now, and I'll refer to a theorem, and I'll probably stop this video for now, but because I've gotten to an ending point. After performing that pivot, I still have a negative indicator, and above the bar here, above the dotted line, I have a 0 and a -3. There are no positive numbers left up inside here. You have to almost get to the end of section 6.2 where you've gone through all of the things that could happen. But this tells me that there is no optimum solution to this problem. So the fact that there's no positive number in the pivot column that I'm trying to pick, this column would be the pivot column. There's no element that I can pivot around. So this problem has no solution. And I think that happens once or twice in the homework problems. You'll look at a tableau, there's a negative number down here, but there's no positive number up above, so you cannot perform another pivot, and there is no optimum solution to this particular problem. I'm gonna, like I said, I think that probably was like my 30-minute limit or so, because these videos kind of take a while. I'm gonna show you that what I was talking about, page 307 in your textbook. There's a flow chart that kind of summarized what I just was saying. And like I said, this is on the last page, just about before you would have started exercises in, pretty much, it's pretty close to the end, exercises in the back of that chapter if you were doing it. So step 1, we wrote the standard maximization problem in standard form, slack variables, and then we put it into the initial system. We wrote the initial tableau. Step 2, are there any negative indicators in the bottom row? Yes. So we selected the pivot column. Are there any positive elements in the pivot column up above the dotted line? Yes, in that first pivot there were. So we picked the pivot element and we performed a pivot operation. Then you go back to step 2 that says, are there any negative numbers in the bottom row? And in this case, yes, there were, but at this step, so we were able to select the pivot column. Then step 4 says, are there any positive elements in the pivot column above? And the answer to that question was no. So stop. This linear programming problem has no optimal solution. So I picked one that didn't have an optimal answer to it to demonstrate first, but sometimes those weird cases, remember, are kind of the strangest ones. I'll make another video where I go through one problem from start to finish, maybe a little more complicated problem, or do a sample homework problem or two, maybe tomorrow. But I wanted to, since Colby asked, I decided to put together real fast tonight a little bit of help starting off chapter 6.2 and trying to help you get to where you could start doing some of that work if you were already there, because Colby was. Anyway, I will visit with you again shortly. I'm going to turn the video off now. It's been fun visiting with you for a few minutes. That's all. Goodbye.